Hi everyone, good morning. A very happy morning to all. We, the Department of Physics, Savita Engineering College, welcome you all to the webinar on the electroanalytical technique of water splitting, the do's and don'ts. Let me now introduce our speaker of the day. Dr. Anantharaj. He is a material and molecular electrochemist working on electroactivities of small molecules, especially in energy and environmental science. He obtained his bachelor's and master's from Presidency College and got qualified in SET and NET and JRF, and he joined CSIR Karakuri for doing his PhD under the guidance of Dr. Sutrada. He was awarded the postdoctoral fellowship from Japan, JSPS postdoctoral fellowship by the Society of Promotion of Science, and he joined the team of Professor Suguru Noda in Waseda University of Tokyo, Japan. He has awarded with ECS India section of S.K. Rangarajan Graduate Student Award for 2017 by the Electrochemical Society, USA. He has 56 articles to his credit with the highest impact factor of 7.2, 36 of first or corresponding author, and 22 published by ACS. He have more than 2,100 citations with an H index of 21. Now let me hand over the session to Dr. Anantharaj.
Yes, thank you, Dr. Priya, for the nice introduction. I'm very happy to join with you all too. I was actually looking forward to it. I'm really happy to share the things that I learned in this field of research among the budding researchers and the established fraternity of faculties of various institutions around the world. And it gives me really immense pleasure to share my works with the members of this meeting. And I would like to start, if you permit. Yes, thank you. So I hope you can see my screen now. Yes. I'll go forward then. Yeah, thank you very much, and I welcome you all once again for my talk. Thank you for joining me today. And today I'm going to talk about a few things about electroanalytical techniques used in water splitting, and things that we must do and we must not do in handling these electroanalytical techniques for water splitting application. So these things I learned from my experience of this past 4 or 5 years of research, and I also wrote a few perspective and review on the same topic, and I would like to share the views. Actually, these are my personal views on how to use these electroanalytical techniques for water splitting. So I hope that this will be useful to all of you. And I request you all to be patient. If you have any question in between, you can raise your hand and request the host to ask me the question, or you can wait until the end of the presentation and you can ask me your questions in the comment box. I will be happy to answer. So please be with me for another 60 to 80 minutes. Thank you. And let me begin. So, yes. So before going deep into the electroanalytical techniques used for water splitting, we must understand one thing first, that why we need water splitting after all. So we know that whatever the energy research that is being conducted all around the world are mainly because of the reason that we are actually running out of carbonaceous fuels, which are nothing but the coal, gas, and oil, as per the estimated amount in the reservoirs. The oil will last only up to 2050, and gas will last only up to 2060, and coal will last only up to 2090 or so. So this is taken from the World Energy Survey, of 2017 to 2050 from the annual report of World Energy Survey, which indicates that we are in a verge of depleting all our carbonaceous fuels. So we need to go for alternative energy driven economy. Instead of carbon economy. So what people are trying to do is that replacing this carbonaceous fuels with renewable energy sources. You can see that in the meantime, when we are experiencing a rapidly increased depletion of carbonaceous fuels, we are also witnessing exponential increase in the use of uh, green renewable energy consumption. You can see that this particular graph. Yeah, wait, I'll change the pointer so you can see. Yes, yeah. This graph shows you how the energy consumption from renewable energy sources are increasing exponentially in recent years. So this is clear that we are on the verge of depleting all our carbonaceous fuel, so we need to go for renewable energy. But we have issues with renewable energy. So that's why we need hydrogen, because renewable energies are not continuous, they are seasonal, intermittent, and they are available only for a few periods of months in a country. Luckily, in India, we have sun for all 12 months in a year, but not all in all other countries. So they need to depend on various other energies like wind, geothermal, tidal, hydrothermal, and solar as well as. So in this case, what we can do is when this energy are available at its peak, and when we can produce excess electricity out of these renewable energy sources, we can use that energy to split water via water electrolysis, which will produce the hydrogen, so-called hydrogen, which is having a lot of promises to be an efficient alternative to that of carbonaceous fuel. So we can store that hydrogen in a storage tank that can be exported for further uses all around the world, and they can be used on demand in hydrogen engine or in a fuel cell. So that can be, and energy can be generated from this, and that energy can be used for domestic and industrial purposes. So upon using this hydrogen in fuel cell and hydrogen engine, the byproduct is again going to be the water. So we will have water for further splitting and producing hydrogen. This is called the very famous hydrogen cycle. So in this area of hydrogen economy, realizing economy, we have three domains. One is that hydrogen production, and second one is that hydrogen storage, and third one is its consumption. That can be either via fuel cell or via hydrogen engine. So there are three domains, and people are actively working on this area, the hydrogen generation, because hydrogen generation is not only because we are going to use it instead of carbon, it is also regarded as a way of storing energy in a large amount, because conventional energy storage devices like batteries, supercapacitors, those devices are not at all capable of storing large amount of energy that we produce from renewable energy sources this day. Because if you just compare the amount of energy that can be stored with a grid made up of lithium-ion batteries or the supercapacitors with the amount of energy that we produce every day from these renewable energy sources, they are nowhere closer to even 1%, which means that we can produce as much as energy as possible, but we cannot store it efficiently. So one way to do is that we can use that excess energy derived from intermittent seasonal energy sources like solar, wind, tidal, geothermal, and we can use that electricity to split water, and water which will produce hydrogen, which can be stored and can be used again on demand using a fuel cell or a hydrogen engine. So this is the overall idea why we need hydrogen as a fuel and why we need water splitting as a mean for producing hydrogen. So to further explain, I wish to list out a few advantages of hydrogen and also the disadvantages. As you can see here, hydrogen is the only element in the periodic table which has highest specific energy, about 142 megajoule per kilogram. So there is no other element which can produce this much energy upon consumption. So undoubtedly, hydrogen is the most efficient alternate to carbonaceous fuels. And we avoid the carbon emission issue here. And the combustion product is, as I said earlier, just water. So we can have a sustained cycle. We are going to split water, make hydrogen, and again combine it with oxygen, make water, and you can do it as long as you wish to do. So we have plenty of water in our oceans to play. So we will not will never literally run out of resource for hydrogen. So this appears to be an ideal and most efficient way of storing energy, as well as generating energy, as well as creating an economy based on hydrogen for sustainable future. But the problem is that here, as you can see here, the relative volume needed for hydrogen storage to achieve 300 miles range of a vehicle, which is run by hydrogen, is in this range. As you can see here, gasoline of 20 gallon is needed to reach 300 miles, which requires this volume. But the liquid hydrogen and chemical hydrogen, hydrates and compressed hydrogen, and these are all requiring more volume than what is actually required by gasoline. So it is a huge issue in the area of hydrogen economy, and people are actively working on storage, and particularly the metal hydrides. They seem to be having a potential storing capacity which can be used to store hydrogen efficiently, and which will also be helpful in realizing successful implementation of hydrogen economy in the future for sustainable development and growth. So now I have emphasized the need for hydrogen energy and hydrogen economy, and I also stated that water electrolysis can be used for hydrogen generation. So what are the other ways that we can obtain hydrogen? So we have, as I said earlier, water electrolysis, and we have steam reforming of hydrocarbons, and we also have photocatalytic and photoelectrocatalytic water splitting. Other than this, we also have some other methods which are all used for on-demand rapid production of hydrogen in a very small scale, like acid hydrolysis of metal hydrides. But we have some issues with other methods, like steam reforming of natural gas requires high temperature and pressure, and most of the time the hydrogen produced is not with the highest purity, which is required by the hydrogen combustion engine as well as by the hydrogen oxygen fuel cells. So what we need is we need a method which operates at ambient condition and can produce hydrogen with the utmost purity. So we have photocatalytic water splitting, which is nothing but the photolysis of water, taking directly the energy from sun and splitting water, which is the most greenest method of all. Yet it is irritatingly slow, in the sense the amount of hydrogen you can produce with a whole day of operation is going to be very, very, very minimum. So you have to spend your lifetime to get your desired amount of hydrogen with photocatalytic water splitting. So people have combined this technique, photocatalytic water splitting, with electrocatalysis, and they made something called photoelectrocatalysis, which you see here. So with this device is capable of producing hydrogen in a faster amount with the help from external applied electricity and also from the light energy. But one issue, there is an issue with this setup, that the photocatalytic activity of this photoanode, which do the water splitting with the help of both applied potential as well as with the help of the solar energy, they tend to lose their photocatalytic activity at high current operations. Like in conventional electrocatalysis, water splitting electrocatalysis or water electrolysis in the broader sense, the cell is usually operated at a high cell voltage or with a very high current density, like 1 to 2 amperes, which are very high current density. At that current density, the electronic properties, which is supposed to help the photocatalytic activity, is no longer the same. So they lose their photocatalytic activity at a high current operation. So photoelectrocatalytic water splitting is not a superior method for producing bulk amount of highest purity hydrogen in shorter time. So we don't have other option other than water electrolysis. So that's why we need water electrolysis. And I have also listed the advantages of water electrolysis. As I said earlier, you can perform water electrolysis, that means splitting of water without requiring any high temperature and pressure. Excess electricity generated from intermittent sources can be used, and the purity of the produced hydrogen is very, very high. You cannot have such high purity hydrogen in any other available method. And we have water, which is going to be the source and which is also going to be the emission product. So we don't have greenhouse gas emission. We apparently do not release any hazardous chemicals into the environment, unless otherwise you are using a corrosion resistant electroactive material. So after all, this is the fastest method known for hydrogen production on the earth. So we need water electrolysis. Yes. So before going into the electroanalytical techniques, I also want to show you something about the thermodynamic aspects as well as the kinetics of water electrolysis and water reduction, which are involved in the production of hydrogen. As you can see that I have mentioned the half cell reaction that is occurring at the cathode and the anode. The overall splitting of water occurs with the energy of change in free energy of positive 237 kilojoule per mole. We all know that when the change in free energy is highly positive, this is going to be a reaction which is requiring an external energy to be applied, right? So we have to apply an energy, then only we can split water. So according to this energy and from thermodynamics, we have calculated that at the reversible potential, where we only consider about the change in free energy, we obtained 1.23 volt versus RHC to be the reversible potential of water electrolysis. But when we consider the entropy change, so which must also be considered for calculating the actual water splitting potential, we have calculated for 25 degree to be 1.48 volt. This is called thermoneutral potential of water electrolysis. This is reversible potential of water electrolysis, and this is thermoneutral potential of water electrolysis. Difference between these two is this is determined only from the del G, and this is determined by taking the entropy factor also into consideration, which means that we cannot split water at 1.23 volt. We need additionally 250 millivolt over potential to start the electrolysis, so which is called the thermoneutral over potential. But there are some exceptions to this condition when we have high mass loading or some 3D electrodes, or if you are operating the cell at high temperature, relatively high temperature, you can achieve water splitting below this potential. So there are some exceptions. You can refer this article where you can find more detail. So we also have kinetic issues beyond thermodynamics. Kinetics plays important role in determining the energy efficiency of these electrocatalytic materials, which we also have to be aware of. So here you can see this. This is taken from the very famous book chapter written by Professor M.T.M. Cooper called Fuel Cell Science, where you can see this particular image includes the reactions, off-cell reactions of both water electrolysis as well as the hydrogen-oxygen fuel cells. As you can see here, this particular reaction is the cathode reaction of water electrolysis, and this reaction is the anode reaction of water electrolysis. And here we have the oxygen reduction reaction, which is the cathodic reaction in the fuel cell. And here we have hydrogen oxidation reaction, which is the anodic reaction in the fuel cell. So the first thing you can notice here is that both hydrogen evolution reaction and hydrogen oxidation reaction, they intersect exactly at its reversible over potential, which means that they are kinetically very facile and they don't need additional over potential to begin this process. So in the case of oxygen reduction and oxygen evolution reaction, we know that the reversible potential for this process is 1.23 volt versus RHC, but in real case, the system requires additional potential to start the electrolysis and additional potential to start the oxygen reduction. This additional potential requirement arises from the fact that OER and ORR are not a simple discharge and deprotonation step like HER. They are actually the reaction which involves 4 proton transfer coupled with oxygen bond formation or breaking, depending on the reaction what you study. If it is OER, you are going to break, you are going to form a new oxygen bond. If it is ORR, oxygen reduction reaction, you are going to form, you are going to break the existing OO double bond via supplying electrons and protons. So this is the main thing that causes this increase in over potential. So this is also going to be the source of energy loss during both water electrolysis and also while combining it in the fuel cell. So while generating hydrogen, you are losing this much amount of energy, and while combining hydrogen with oxygen, you are also going to lose this much of energy. So in the overall process of hydrogen generation and combustion, you are actually losing this much of energy. So this is one of the reason why Elon Musk, we know him, an entrepreneur, he called this mind-bogglingly stupid because we are losing so much energy in this process. While generating hydrogen, we lose some amount of energy, which is significantly high, and while generating energy from hydrogen in fuel cell, we are again losing some amount of energy. And this have something to do only with the reaction that is involving oxygen in both cases. There is no kinetic issue with hydrogen evolution and hydrogen oxidation. So this thing we have to remember, and this will be useful in evaluating the electrocatalytic performance of many materials, and it will also be useful in understanding how one should use the electroanalytical techniques for characterizing their materials for electrocatalytic water splitting. And one more thing that you should understand here is that in the case of hydrogen evolution reaction and oxygen evolution reaction, you don't see any mass transfer limitation because they are kinetically controlled irreversible reaction where the product is escaping from the solution. So in practice, you literally do not letting the diffusion layer to grow. I will explain in detail in the further slides what is a diffusion layer and how it affects the shape of the voltammogram. And in this case of hydrogen oxidation reaction and oxygen reduction reaction, you have a gaseous reactant getting reduced and producing water, which means that the product is accumulating on the electrode surface, and its generation limits the further diffusion of oxygen to get into the electrode surface. So there is a mass transfer limitation. And the same is the story in hydrogen oxidation reaction, where you are oxidizing the gaseous hydrogen into proton, which is going to be in the solution near the electrode surface, which will be forming a diffusion layer. So this will also going to limit the reaction rate. So the HOR and ORR, they are mass transfer limited reaction, but HER and OER, they are kinetically controlled, irreversible, charge transfer limited reactions. So please keep this thing in mind. So this will be helpful when I explain about the electroanalytical techniques and how to interpret the data. So now we have successfully come to know about the basics of water electrolysis and why we need water electrolysis, and why hydrogen is very important for attaining a sustainable future in the energy sector, and why water electrolysis is superior to other methods. And we also learned the basics, thermodynamics and the kinetics. Now we have the evaluation perspectives. So in this case, now we are very clear that water electrolysis is an energy consuming process, and we certainly need catalyst which can reduce the energy loss. So we are going to screen as many as materials possible which will have highest activity, highest selectivity with the utmost stability. All these three characteristics are very important in order to qualify a catalyst for commercial water electrolysis application. So what we do in evaluating water splitting, electrocatalytic water splitting, is we will measure the activity in terms of overpotential, which can be calculated from the current density normalized using the geometrical area or the mass of the catalyst or the specific activity. And we also have TAFL analysis, from where we'll get TAFL slope and external current density, which will give hints on the intrinsic kinetics of the electrocatalytic kinetics of the electrocatalyst to catalyze the electrocatalytic reaction. And we also have turnover frequency, which is nothing but the measure of the amount of products which is going to be produced per unit time. And we have Faraday efficiency, which is a selectivity parameter, which shows you how efficient your catalyst is in using the applied energy selectively for the desired reaction, which means that the applied energy is not going somewhere. So applied energy is being used for the reaction, what we intend to do. So that is determined by the Faraday efficiency. So apart from these three activity things, we also have stability, which is very crucial in order to make the water electrolysis process for hydrogen generation commercially successful. So which is done by accelerated degradation condition and prolonged galvanostatic and potentiostatic electrolysis, which is nothing but chronopotentiometry and chronoamperometry. And the accelerated degradation condition is nothing but sweeping the potential on the electrode surface at a very high scan rate. So apart from this thing, we also have a EXA and EAI study, which will be used to correlate the activity trends kinetic and thermodynamic activity trends that we observed for a given set of catalysts. So we have this many evaluation perspective. So we are going to see each one of them and how they are determined from their respective electroanalytical technique and the data obtained from it. And there are certain things that we cannot do, which is against the ethics. And there are certain things that we must do in order to ensure that there is no more unknowing error made. Unknowing errors are being made in the field of water splitting electrocatalysis. So that's what my intention of this talk. And we have these electroanalytical techniques. We have cyclic voltammetry and linear sweep voltammetry. These two techniques are used in over potential determination, which is a very important parameter in saying the efficiency of an electrocatalyst. And we also use this for extracting Tefel plots. We also use this for calculating electrochemical surface area on electroactive sites, and also to test stability under potential dynamic conditions. Note this is potential dynamic condition. And we have chronoamperometry and chronopotentiometry, which are mainly used to study the stability, the endurance of the catalyst. But these can also be used to derive Tefel plots, which are more precise than the Tefel plots that would be obtained with cyclic voltammetry and linear sweep voltammetry. And apart from this chronoamperometry and chronopotentiometry data photocalorimetry and gas chromatography. I will explain it later. And we finally have the most powerful techniques. I'm sorry, I'm having some issue with my internet. So, Dr. Priya, can you hear me?
Yes.
Yes. Yeah, thank you. Yeah. So we have electrochemical impedance spectroscopy, which is an alternating current technique. Unlike chronoamperometry, chronopotentiometry, and cyclic voltammetry, linear sweep voltammetry, electrochemical impedance spectroscopy is an AC technique, which is very powerful tool in examining the short sensor process at an interface, which will be used to correlate the activity trend for a given set of catalyst and also to extract Tefel blood. I'll tell you one thing, that the Tefel blood, which is going to be obtained using electrochemical impedance spectroscopy, will be the most appropriate one when compared to this one and this one. I'll explain why and how later. And we can also get EXA in catalytic turnover condition using electrochemical impedance spectroscopy, which cannot be obtained using cyclic voltammetry or linear sweep voltammetry. So I will be talking about these techniques and the things that we must do with these techniques and we must not do. So this will be the remaining things about this talk. So let's go into some basics of the cyclic and linear sweep voltammetry. As you can see here, voltammetry is nothing but studying the response of an interface in terms of current as a function of potential, which we know. Yes. So interface in the sense it can be anything, a solid-solid interface or a solid-liquid interface or liquid-liquid interface. Only thing that you need to have is a rigid connection to the electrochemical workstation or the thing which you use to measure the response. So here we have the first image, which says that in linear sweep voltammetry in LSV, we are sweeping the potential from a point V1 to V2 with the time, with time, and we reach potential V2 at certain time. Okay, so during this sweeping of potential, what happens to the interface? So that can be obtained from the current response. So to know that, we have a plot called voltammograms, in which we plot the voltage and current in X and Y axis, where we can see that when you sweep the potential from V1 to V2, you are actually seeing an increase in current density, and which attains a maximum, and it starts to decay and it attains the plateau at V2. So why this appears? So why this peak-shaped voltammogram appears, and why there is an increase in current, and what happens? This can be used to infer the charge transfer characteristic of your interface or the nature of electrocatalytic reaction that is happening at your interface. So in the case of cyclic voltammogram, what we additionally do is we are not only sweeping the potential in the forward direction, we are also reversing the potential back to the starting point with the same scan rate, I mean the speed of change in potential, and to attain the initial potential. In this case, in addition to the curve, what we observe here, we also will have another curve here. So this is typical peak-shaped voltammogram, cyclic voltammogram, which can be obtained with a solution of electrode containing electroactive species under no externally influenced mass transfer condition, which means that you are performing the reaction at static condition. So you are not stirring the solution, you are not applying ultrasonic works, you are not rotating the electrode, you are not doing anything. You are just inserting the electrode and recording the voltammogram with just sweeping the potential. So this is what we have. And for a reversible reaction, a completely reversible reaction, for any change in potential, there will be an equilibrium established between the electroactive species which are involved in this reaction. If you are studying about a redox reaction, we can simply represent like the oxidized species or reduced species, and the ratio between these two will affect the cell potential. And we can also get to know about the standard electrode potential when these two are in the same concentration. So this can be used to study various property of the interface, which will be useful in knowing the interface characteristics as well as the nature of the electrocatalytic reaction occurring. So we also have to know why do we see a peak-shaped voltammogram. So what causes this peak-shaped voltammogram? This thing is very important in understanding fundamental electrochemical response of an interface. So we have several situations. Let's just start with this. So we are starting at point A. At point A, the potential E1, and we are reaching potential E2. That is the point D. Here you can see, and we are again coming back to point G, where we are reaching the potential E1. So during this, you are seeing cathodic peak and then an anodic peak. Please be careful that this particular CV is given in the US convention, where they use the reduction current in the right-hand side and the oxidation current in the left-hand side. So this is actually reduction peak, and this is actually the oxidation peak. So in this case, we have a few things that we must see before going in detail. So we have point C, which is called the cathodic peak potential, and point F, which is called anodic peak potential. And we have a potential which is in between these two, which is called E half, which is something mentioned here, where the concentration of oxidized species and the reduced species are the same. So the peak-shaped voltammogram appears because of the development of a diffusion layer. So diffusion layer is something which I have given here, as you can see here. This is when you insert an electrode, the first thing that happens in the solution is that the oppositely charged ions in the solution will get adsorbed on the surface, and they will form a layer. And we have studied in fundamental electrochemistry about this diffusion layer formation, which are further divided into several categories like inner Helmholtz plane, outer Helmholtz plane, and diffusion layer, which I don't want to go in further. So this is very important in understanding the peak-shaped voltammogram. As you can see here, at point A, when we don't have any change in potential, the concentration of reduced species. You should consider this reaction for following these events. So the ferrocenium cation is being reduced by the injection of an electron to ferrocene. So the green line is indicating the concentration of ferrocene, and the blue line is indicating the concentration of ferrocenium cation. So at point A, where we have not applied any potential, the concentration of ferrocenium cation is almost 100%. That is close to unity, 1. But the reduced species is 0. So when you increase the potential and reach the point B, which is nothing but the E half, where the oxidized and reduced species are in exact equilibrium and the concentration of the same of both are the same. So there we have established an equilibrium at which both the oxidized and reduced species are in the same concentration. So at this point, so these two are in the same concentration. So for the further reduction in the current, which can be observed, or I can say which will be dictated only by the unreduced ferrocenium cation that are diffusing from the solution to the electrode surface. So that is why after this point, we are experiencing a reduction in current, gradual reduction in current. This reduction is indicating this layer, diffusion layer is growing, is keep on growing. As you can see here, at this peak, the concentration of the oxidized ferrocenium ion is lower, but the concentration of reduced ferrocene is higher, which means that the electrode surface is being saturated with the reduced species, which means that it is forming a diffusion layer beyond which the electroactive species, which is nothing but the ferrocenium cation, has to diffuse through and reach the electrode surface for further reduction. That is why we observe a reduction in the current in this region. So once we reach point D, what happens is this diffusion layer thickness, as you can see, this diffusion layer thickness is increasing with increasing potential. So once we reach point D, the further current, whatever being observed as a result of reduction of ferrocenium cation, is only depending upon the number of electroactive species that are diffusing from this area to the electrode surface. So that is the reason why we see this one. So in some cases, you will even see a very horizontal plateau, which means that the diffusion layer is no longer growing and the applied potential is no longer affecting the growth of the diffusion layer. So the amount of electroactive species which is being reduced, diffusing towards the electrode surface is the same. So what we do next is that we are reversing the potential from the point D to point E, the E of anodic reaction, where we see again equilibrium established between the reduced species and oxidized species, which is something similar to this one. So we have a first intersection between these two concentration, within the concentration of these two species, which is caused by the reduction and reduction EF, and this is caused by the oxidation EF. So when you further increase the oxidation potential, this collapse and the concentration try to restore its original state, but it cannot happen so, because the first interface created, concentration gradient interface created as a result of reduction, will remain at this distance of diffusion layer. So this is the reason why we see a peak-shaped voltammogram. So in conventional studies where you don't apply any external mass transfer mechanism, this is the one you should expect always from your electrochemical cell and its response. So there are some exceptions when we cannot see such kind of peak-shaped voltammogram, which are when we use microelectrodes, or when we use rotating disc electrodes, or when we strip the solution. So typically, I can say when you affect this diffusion layer formation, you will not see all this thing. So I think I have made it clear why we have seen a peak-shaped voltammogram. So let's see about the effect of scan rate and reaction rate, what they can do to the peak-shaped voltammogram and what we can infer from it. So one thing that we need to understand is that many of us know increasing scan rate will increase the current, peak current. This is true only for the reactions which are controlled by the diffusion of the electroactive species, but not for the reaction which are controlled solely by the charge transfer. So I will explain it here. So this animation, as you can see, it is showing the increase in scan rate when you have higher time, which means that you are sweeping the potential with the slower scan rate. When you have very shorter time to reach the potential V2, you are sweeping the potential with a very faster rate, which means that you are letting the system to attain a thick diffusion layer formation. When you sweep the system with a very low scan rate, you are giving enough time to the interface to form the diffusion layer, thicker diffusion layer, which means that you are not allowing enough electroactive species to get oxidized or reduced here. But when you do sweep the potential very quickly, you are not allowing the system to form a thick diffusion layer, which means that more number of electroactive species can diffuse, because the diffusion layer thickness is very, very thin in the case of higher scan rate. So you are seeing an increase in peak current. So this is the reason why scan rate is very important, and we also should mention the scan rate. And there are other things that can affect the peak current as well as peak potential. One of such important thing is the rate constant of the reaction. If this can be observed only when the reaction rate, the electrochemical charge transfer reaction rate, is very faster than the scan rate. keep in mind that the scan rate should be slower than the reaction rate. What if the reaction rate is very slower than the scan rate? Which means that you are affecting the equilibrium and you are also affecting the diffusion layer thickness. So when you have decreased rate constant, the peak potential will shift towards the anodic side, or if it is the reduction towards the cathodic side, and also there will be change in the peak current. So from the shape and peak potential with respect to scan rate, you can determine whether the reaction is reversible or irreversible, or even the rate constant is different or not. So the same is true in the case of cyclic voltammogram also. You can see the cyclic voltammogram also showing a similar increase in current, and this increase in current with respect to scan rate can be related using a very famous equation, which is the Randall-Sevik equation, which relates the scan rate, square root of scan rate with the peak current. So if you want to know the type of electrocatalytic reaction that is occurring on your electrode is reversible or irreversible, or occurring through adsorption or adsorbed layer, you can use this plot of peak current against square root of scan rate, which will give you a linear response if it is truly reversible reaction. So if it is irreversible, it will not be. So in the case of irreversible reaction, you will have linear increase with just scan rate, not with the square root of scan rate, with just scan rate. And also, if it is, there can be two other reasons. Not only the irreversibility of the reaction, which will affect this linear relationship between the square root of scan rate with peak current. And there is one more thing, that is the reaction could be occurring through adsorbed species, which I will not talk here. I will be talking about this much in my upcoming webinar. So if you are interested, you can join there, and I will be happy to explain all this thing in detail. So now we know what is cyclic voltammogram and linear sweep voltammogram, and for a diffusion controlled reversible reaction, how the shape would appear and how the shape would change with increasing scan rate and decreasing rate constant and other thing. So I have listed something here, the characteristics of reversible reaction. In this case, the peak to peak separation. I'm talking about this, the cathodic and anodic peak to the separation between these two peak, which should be around 59 millivolt, and where the N represent the number of electron transfer involved in that reaction. And the peak position is scan rate independent. Peak position should never change. If it is a reversible reaction, you can see the peak position is never changing if it is a reversible reaction. If it is irreversible or quasi-reversible, or with a different rate constant, it will be changing. So one more thing is that the anodic and cathodic peak current ratio will always be equal to 1. So you will never have different ratio value. So if your reaction satisfies all these conditions, you can clearly say that your reaction is completely reversible, both chemically and electrochemically. Yes. Now we are entering into the picture of water electrolysis. So I have explained how cyclic and linear voltammogram could appear when we have diffusion control reaction. But water electrolysis and the Hassel reactions of water electrolysis, the so-called oxygen evolution reaction, OER, and the hydrogen evolution reaction, HER, they are not diffusion controlled reaction. The first thing which we must know, which means that it will never result in peak-shaped voltammogram, because they are totally controlled by the charge transfer of the process. Okay, so we have here, I have here listed out the characteristic of an irreversible reaction. They never result in peak-shaped voltammogram, and current remains constant irrespective of the scan rate. If you increase the scan rate, and the current will never change. But in the case of diffusion control reaction, you have seen that the current will increase. And so only thing you can come to know here is that as long as you increase the potential window, you will still be witnessing increasing exponential increase in current density. So this will tell you whether your reaction is reversible or not. So examples of this kind of irreversible reactions are, of course, water electrolysis, Hassel reactions of water electrolysis, and electrolysis of molecules that result in gaseous products. Because in the previous case, when I explained about the peak-shaped voltammogram of diffusion control reaction, I showed that the reduced product is accumulating on the surface and creating a diffusion layer. But in this case of OER and HER, the reduced or oxidized product are going to be hydrogen or oxygen gas which are escaping out of solution. So they are not creating any diffusion layer for the electroactive species to wander through. So there is no issue of forming a diffusion layer. So they don't have any issue in reaching the electro surface for further reaction. So that is why we are not seeing any peak-shaped voltammogram in the case of OER and HER. And this current is totally irrespective and then of scan rate, and they never change with scan rate. So this is an example of NaFLDH, and this is an example of stainless steel scrubber, where you can see that the oxidation of the material is diffusion limited, but not the OER and HER. So this is something that we need to understand. And again, there are some exceptions. Water oxidation and water reduction can be diffusion limited in certain cases, like neutral water splitting and water splitting in neutral and near neutral waters. So which will be introduced later. And we have chronoamperometry and chronopotentiometry. As I said here, these are static method, while CV and LSV are dynamic methods. In CA, we are studying the response of the interface in terms of current as a function of time at a fixed potential. That is very important. So that's why it is called chronoamperometry, because we are measuring the response of the interface in current with respect to time. So in chronopotentiometry, we have potential which will be monitored as a function of time at a fixed current. So this is a typical example of a chronoamperometry response, so where you can see the blue line, the Faraday current, and the red line, the capacitive current. The current response of chronoamperometric plot can be related using the very famous Cottrell equation, which I think you can see the equation here. Yeah. The Cottrell equation, which states change in current at any time with a square root of time. So which means that you can literally distinguish between capacity current and Faraday current just from the response, IT response of a chronoamperogram. If you plot the square root of time, it will be linear. And if you plot the square root of time for capacity current, it will not be linear. So from which you can easily determine which part of your chronoamperometry is corresponding to your Faraday reaction and which part of your chronoamperometry is corresponding to the capacitive current. So in the book of Alan J. Board and Faulkner, it is mentioned that one can blindly use 93 lost the final 93% of the chronoamperometry response for calculating the charge transfer rate and the amount of product formed and the Faraday efficiency and other things. So I would recommend to never use or infer the data which you will obtain immediately after starting your chronoamperogram. So kindly refer the book, the Electroanalytical Methods by Alan J. Board and Faulkner, which will be very useful in understanding this thing. So this is the thing. Again, this chronoamperometric response, which I have shown here, is characteristic to that of a diffusion controlled reaction. In the case of water splitting, we are not having any diffusion control process. So what we will see here is a same response over time of several hours. So why we will use this one here is that to test the stability. So if your catalyst is stable enough, you will have witnessed the same current density in chronoamperometry for a very longer period of time, the same potential in chronopotentiometry for a very longer period of time. So this is the reason why we use CA and CP to test the stability of an electrocatalyst. And I will tell you something that this is the most optimal and most suitable one for testing the stability of an electrocatalyst for a water splitting electrocatalysis, because in real water electrolysis, no one is splitting water with a potential cycle. They just apply a constant current or they just apply a constant potential, which is usually as high as 2 volt or as high as 1 to 2 ampere per centimeter square. So testing the stability of an electrocatalyst under this condition is more appropriate than testing the electrocatalyst stability under potential dynamic conditions, such as cycling the potential with very high scan rate for a very large number of cycles. I would say it is just meaningless. Yes. And we have electrochemical impedance spectroscopy. And as I have introduced earlier, this is an alternating current technique which is capable of reflecting the charge transfer properties with no issues of IR drop. We know that all DC technique, whatever the direct current technique which we use in electroanalytical chemistry, they all suffer from IR drop, which is nothing but we can also say it can also be termed in other words like ohmic drop or potential drop, something like that. So this is being a method which is not affected by IR drop is an effective tool in learning the interface characteristics. So what we do here is, in principle, we let the system to sit in a constant potential, which can be 0 volt versus the reference electrode, or 0 volt versus the open circuit potential, or it can be the potential, it can be the open circuit potential itself. So we are letting the system to sit on a constant potential at a fixed potential, and we are applying a perturbation, AC perturbation, alternating current perturbation potential, which will have magnitude from as low as 5 millivolt to 1 volt. This solely depending on the purpose what you are using for what we are using for the material. So if you are studying the electrocatalytic properties of a set of material which have activities closer to one another, and the activity difference is only by 10 to 20 millivolt difference, I would suggest you to go with a minimum perturbation potential magnitude such as 5 millivolt. But in the case of corrosion studies, we all know that impedance plays a key role in corrosion prevention studies, where people used to measure the charge transfer characteristic of the interface or the coating or a paint which is coated on a metal surface over a long period of time. By applying this technique, what they usually do is they will perform the experiment in OCV, or open circuit voltage they call, because it is technically a 2 electrode system. So they will apply AC perturbation potential of 500 millivolt to 1000 millivolt, which means that it will oscillate the potential from the OCV with a potential window of 1 volt, 500 millivolt to 1 volt. So even when the potential shifts from the OCV to this extent, they should show that there is no charge transfer occurring, and for a charge transfer to occur, the resistance should be very, very, very high. So this is the reason why people use electrochemical impedance spectroscopy in corrosion prevention study, just to show that their surface or interface is very resistive towards charge transfer. So as I said earlier, electrochemical impedance spectroscopy is a versatile technique. It can be used for so many other things. Particularly in the case of water splitting electrocatalysis, what we do here with this technique is that we use this mainly to correlate the activity trend of a given set of catalysts. So we will see how we are doing that one. In this case, the applied potential can be expressed in this way, and the response is expressed in this formula, and where the component theta or sometime phi will be used, which indicates the phase shift. In electrochemical impedance spectroscopy, impedance of the system, of the interface, and phase shift, these two are very important parameters which are used to learn the characteristics, charge transfer characteristics of the interface. So what is the difference between impedance in an AC circuit and in a DC circuit? That we must understand before going into the detail. And impedance is nothing but a collective opposition to opposition exerted against electron flow, not only by the resistor but also by the capacitor and inductors, which we will be having in an AC circuit. But in DC circuit, we don't have capacitors and inductors. We have only the resistors. So there will be only the resistor. Impedance of the resistor will be impeding the flow of electrons. But in the case of AC circuit, we will have capacitors and inductors, which means that by analyzing impedance spectroscopy, we can come to know about the capacitive characteristic and inductive characteristics of our interface, which will give a valuable, invaluable information about the electrocatalytic properties of our interfaces. So in AC circuits, as I say here, there are capacitors and inductors, and in addition to that, there could be diffusion. But again, I'll remind you that this diffusion component is important only when we are examining the diffusion control reactions, such as the one I explained earlier. But in our case, that is in water splitting electrocatalysis, these are not diffusion control reactions. So we will not have this issue. So we are interested in the phase shift and the impedance. So which we will see in the next slide. Yes, the circuit elements and their characteristics. This is something important in understanding the electrochemical impedance spectroscopy. So we, in the case of water splitting electrocatalysis and the corresponding oxyl reactions, as they are totally charge transfer control reaction, we'll have only these three circuit elements. And the first one is resistor, and the second one is capacitor, and the third one is inductor. This is witnessed in the case of materials that are highly active for the particular electrocatalytic reaction, or the materials which have high density of states in the reversible potential. So these three are very important in understanding the electrochemical impedance measurement that are made with this kind of reaction. Before that, I'll just explain this thing. In the case of resistor, it has no imaginary part. I believe that you people know about the imaginary and real part of impedance, because this comes from the vector analysis and the complex number analysis of impedance spectroscopy, where the factor square root of -1 is used to visualize the interface characteristic in impedance spectroscopy. So a resistor has no imaginary part, it has only the real part of impedance, and it exerts zero phase shift between potential and current, which is something like this. There could be change in magnitude of the potential and current, but they never change in shift. They fall in the same phase. In the case of capacitor, they has no real part, but they has an imaginary part which varies inversely with frequency, which means that at high frequency, the impedance, or I can say the resistance by the capacitor will be very, very, very low, because it is varying inversely with the frequency. So when we have high frequency of AC perturbation, the capacitor impedance due to capacitor will be very low, or it can be zero as well. And the important thing is that it exerts 90-degree phase shift between current and potential. And in that case, the current will always lead the potential in the circuit, like the one we shown here. The current, the red line is showing current and the blue line is showing potential. The current will always lead the potential, because the imaginary part of impedance varies inversely with the frequency, which means that at higher frequency, it acts as a short circuit and there will be a free flow of current. So that's why current always proceeds beyond voltage. In the case of inductor, we know the difference between capacitor and inductor. So inductors store the energy, applied energy, in the form of magnetic field, which will also impede the flow of electron. We know that electron flow can be impeded by the electric field as well as magnetic field. If you have an inductor element in your circuit, so that will also impede the flow of electron. So it is also important. But in some cases, in the inductor impedance due to inductor is used to say the superiority of your electrocatalytic materials, which is also indirectly indicating that your material is having high exchange current density for the said reaction. And it also has no real part, but the imaginary part of this impedance varies, increases with frequency. Unlike capacitor, it increases directly with the frequency. So at a high frequency, the impedance due to inductor will be very high, but in the opposite direction. You must remember this one. And it also exerts 90-degree phase shift between current and potential, and to the opposite direction, exactly opposite direction to that of capacitor. So it will be potential leading current. So it at high frequency, it acts as open circuit, but the capacitor acts as short circuit. At low frequency, inductor acts as short circuit, but the capacitor acts as open circuit. So in both cases of high and low frequency, either this has become short circuit, enabling flow of charge transfer easier, or this is at high frequency, this is becoming a short circuit, enabling the flow of charge transfer high. So in water splitting electrolysis, what we usually do is that we measure the RS, the solution resistance value, the beginning point of the impedance spectra, the Nyquist plot, and which is observed at the high frequency, and the end point of the semicircle at the lowest frequency. At both, there is a short circuit from inductor and capacitor, indicating that they are removed from the circuit and only the resistor is valid. So which means that just by adding the solution resistance, just by subtracting the solution resistance from the overall resistance measured from the end point of the semicircle from the lowest frequency, you can calculate the charge transfer resistance. And this is very important in understanding the application of impedance spectroscopy in electrocatalytic water splitting. And these are the types of plots that are used in electrochemical impedance spectroscopy. And the plots what I have given here are are typical for controlled, kinetically controlled. That means the charge sensor controlled irreversible reactions, where you can see, and this is the so-called Nyquist plot, in which we plot the real part of impedance against the imaginary part of impedance, which shows a semicircle, a depressed semicircle. But in real case, if we have a pure CDL, double layer capacitance, capacitor, it will be exactly equal. So it will be a exact semicircle. But in this case, you can see that it is a slightly depressed semicircle. It is the one what we usually observe in practice. And this is Bode impedance plot, in which we plot the modulus of impedance against the angular frequency omega, log of angular frequency omega, which is nothing but the 2 pi f, where f is in hertz. From these two figures, we can obtain two important values, that is the starting point Rs, and here the resistance which correspond to this horizontal line is Rs. And the first point where it takes the diversion is the maximum resistance here, and the difference between these 2 points is RCT. And here also the same, the difference between these 2 points is going to be the RCT. And here we have something called a Bode phase angle plot, where we can come to know about the nature of charge transfer, whether the system is capacitive or resistive or controlled by charge transfer, so many other things, which is actually the plot of phase angle. And please be reminded of the sign. This is for obtained for an HER reaction, so I used the negative of phase angle, and which is plotted against the log of angular frequency. So yeah, those are the different types of plots used in kinetically controlled reaction. And here we have Nyquist plots for different sets of circuit elements. So we can have solution resistance or uncompensated resistance with a charge sensor resistance, which are connected in series, in which the charge sensor resistance is in parallel connection to the double layer capacitance. More precisely, the constant phase element, which is expressed with the symbol of Q. This is said to be constant phase element because in practical, no one can have a ideal planar surface of electrode. So when you don't have such an electrode, you don't have to say it is CDL. You just have to term it as constant phase element. So we can have this kind of circuit element when you have only one interface, and when you can have this kind of circuit elements and when you have two interfaces. And this is the case when you have only the electrodes performing the desired electrocatalytic reaction, and you will be having this kind of Nyquist plot with two semicircles. And this semicircle is expanded here, you can see, with two semicircles, of which one is corresponding to the response of the substrate electrode, and another one is corresponding to the response of the electrocatalytic reaction. So these two are very common in water splitting electrocatalysis. This is very common when you use the electrode material directly grown on a substrate electrode. This is very common when you use an electrode material coated or modified with the conventional techniques on a substrate electrode like graphite or carbon or some other substrate electrode. So these two are very common in water splitting electrocatalysis only when they are conducted in extremely high acidic condition or extremely high alkaline condition. But in the case of neutral water splitting, as you can see here, you will have the diffusion process, because in the case of neutral water splitting, you will be having two different species, neutral and near neutral water splitting. So in the case of near neutral water splitting, for example, in 1 molar sodium bicarbonate, you will be having both hydroxide ion as well as water molecule. So the first semicircle, what you see here is due to the oxidation or reduction of water molecule, which will be limited by the diffusion of the same through hydroxide ion diffusion layer. So if you want to learn more about this diffusion control process in neutral and near neutral water electrolysis, you can read my review. There you can get more idea. But in most cases, when you do perform water electrolysis in 1 molar KOH or 0.5 molar H2SO4, these two are the typical Nyquist plots that you will end up. So now we have seen some basics. So now we will see how appropriately this can be used. These techniques can be used. Let's start with over potential determination and the convention used in water splitting. We know that every electrode confined reaction has its own standard redox potential, and any potential that is required beyond that standard redox potential is known as overpotential. So in the case of O here, we have shown that it is 1.23 volt. In the case of HER, it is said to be occurring at 0 volt versus RHC by convention. So the main convention used in water splitting electrocatalysis is you need to determine the overpotential of an electrocatalyst at 10 milliampere per centimeter square. And there are huge controversies against this convention, which I will be talking later. And this is the main thing for what the CV and LSVs are used for. So we are going to determine overpotential at 10 milliampere per centimeter square, not at the onset, because onset potential, overpotential does not give you a meaningful comparison. So we also have another issue. I said that we are going to determine the overpotential at 10 milliampere per centimeter square. In that case, you must show the overpotential of an electrocatalyst with a voltammogram, cyclic voltammogram or linear sweep voltammogram without IR drop compensation. Because in real cases of water electrolysis, no one is going to be performing IR compensation. IR compensation is, I will say, it is a bogus thing. It is to show or overwhelm the activity of an electrocatalyst. The only reason that you must perform IR drop compensation in linear sweep voltammogram with linear sweep voltammogram or cyclic voltammogram is that only if you want to use that voltammogram for extracting taffel plot, because taffel plot is by definition said to be plotted with IR drop free overpotential. So that should be the only reason why you are performing IR drop compensation with LSV and CV. It should not be the reason that you want to show your overpotential overwhelmingly low just by performing IR drop compensation, which is not good. So I would advise you to use the IR drop uncompensated potential, which is something I have shown here, the same catalyst. You can see the difference here. This is before IR drop compensation, and here this is after IR drop compensation. This difference occurs because of IR drop compensation. Actually, this IR drop compensated potential is meaningless because you are not compensating IR drop in real case of water electrolysis. So it is always better to include this value without IR drop compensation. And I will also let you know what is IR drop first. As I said that in every solution of electrolyte, they have electrolytes, they have its own intrinsic resistance. And not only that, there's a circuit, what we have, the electrode, the connections that we make with the electrochemical workstation, with the electrode and the electrolyte, all together they have a resistant component which is called uncompensated resistance, which cannot be compensated by any means. So this resistance will always cause a lowering in potential, which is known as IR drop or potential drop. So this must be compensated only when, as I said earlier, you are using these voltammograms for taffel plot extraction. So we can do this IR drop compensation by two methods. One is by digitally calculating, that means manually, by multiplying the RU value of the current and subtracting it from the respective potential. The second method is there are some electrochemical workstation which can perform this IR drop compensation on its own simultaneously, which can also be used to avoid this issue. So I will be discussing about the advantages and disadvantages of these two methods in calculating our potential. Now, I just want to show how this IR drop compensation and the percentage of IR drop compensation could be very decisive and very detrimental in showing the electrode performance. As you can see here, this is an LSV response of RuO2 electrode, RuO2 modified electrode. As you can see, the blue cyan line is without any IR drop compensation. And I have increased the percentage of IR drop compensation as 10, 25, 50, 70, 90, and 100. You can see that, for example, at 40 or 50 milliampere per centimeter square, the potential difference between the IR drop uncompensated RuO2, response of RuO2, and IR drop compensated RuO2, the potential is very, potential difference is very high. So if you give only the LSV that are corrected for IR drop compensation for 100%, you will be overwhelmingly reporting your catalyst with false data, because no one knows what is the actual potential. Without IR drop compensation, the catalyst is able to deliver this current. So which is very important in practical water electrolysis. So I would suggest, so if you are performing iron drop compensation and calculating over potential, please mention the percentage of iron drop compensation and also mention the reason why you have performed this iron drop compensation. So there is one more problem. When we have a catalytic electrode which can perform current as high as 500 milliampere per centimeter square. This is a classic example I have shown. In the previous case, the maximum current was about 70 or 80 milliampere per centimeter square. In this case, it is around 500 milliampere per centimeter square. So when you perform iron drop compensation manually, in this case, the RU was 1.9 ohm. So when you perform 40% iron drop compensation, the potential is somewhere here for the same current density of 500 milliampere. So the potential difference you can see. So would you accept this value? If you are interested in applying this, but if I have reported only this curve in my paper and say that this catalyst is able to deliver this much current density at this potential, and this could be a better catalytic interface for OER, and you are using this material for your real water electrolysis, and you are seeing this potential somewhere there, would you accept this data? So that's what I'm talking about. So reporting IR drop uncompensated over potential is very important. So one more issue is that when you perform IR drop compensation more than 40% in this case, so it is going to be even problematic with catalysts which are delivering current density as high as 500 or 1 ampere even. So in this case, your catalyst, as per your IR drop compensation data, your catalyst is delivering 50 milliampere at 1.5 volt, but 500 milliampere at 1.45 volt. Would you accept this value? So this is the thing I am talking about. So IR drop compensation is important only when you are using this data for TEFL plot extraction, not when you are making or reporting your over potential. Please be reminded of that. And here are the things about the manual and electrochemical workstation corrected IR drop compensation. Here I have taken the same catalyst NiFi LDH with 90% IR drop compensation. As you can see, this is digitally done manually by taking the RU value, uncompensated value, the potential difference between the IR drop compensated and IR drop uncompensated LSV at 50 milliampere is 59 milliwatt. And this is for the same catalyst. The IR drop compensation was performed simultaneously by the electrochemical workstation. You can see the potential difference is 104 milliwatt. So which is true? We cannot know. The electrochemical workstation is telling that after IR drop compensation, you are experiencing 104 millivolt lowering in over potential for a current density of 50 milliampere. But from the RU value, which the calculation I have done manually using the simple Excel sheet, which is saying that the lowering in over potential is 59 milliwatt. So there is a clear disagreement between these two methods. So this indicates once again that IR drop compensated over potential is, I would say, in my personal opinion, is a bogus thing. So you must always report IR drop uncompensated over potential. So next we will go to the TEFL analysis. Yeah, TEFL analysis is a important thing in all electrocatalytic study, which will give you information about the kinetics and the mechanism of the electrocatalytic reaction which is occurring. So first of all, we will see what is TEFL mechanism. So TEFL analysis, we all know this very famous Butler-Walmer equation, which is basically relating the current, observed current of an electrochemical cell with the anodic and cathodic component of over potential, which this is applicable only in the region where the current varies linearly with the potential. Please remember this one. This is applicable only where the current linearly varies with the potential. But this cannot be applicable when the increase in current with the potential becomes exponential with respect to potential. So in this case, this reaction takes the form of TEFL equation. This is for cathodic reaction, and this is for anodic reaction, and the anodic component of this reaction becomes highly negligible, and cathodic component of this reaction becomes highly negligible. So we have simplified the Butler-Walmer equation for at a high over potential approximation using the TEFL equation. So when you plot the log current density against over potential, remember that this Butler-Walmer equation and the high over potential approximation, that is the TEFL equation, are derived keeping an assumption that this over potential is free of IR drop. So it is free of IR drop, and that is why I keep on telling in my previous slides that you should perform IR drop compensation only for plotting TEFL plots from the voltammograms, not for reporting over potential. So this is the reason, because this over potential mentioned here is IR drop free. So when you plot the IR drop free over potential against the log current density, you will get a linear line, and the slope of which is equal to this value, where alpha C and alpha A are the charge transfer coefficient, and N is the number of electron transfer per molecule of product formed, and F is the Faraday constant, and R gas constant, and absolute temperature, which we all know that one. So one important thing is that from TEFL slope, if you are performing at the ideal condition, from TEFL slope value, you can actually predict the number of electron transfer that is occurring on your interface. For example, because in most of the cases, the charge transfer coefficient is always going to be 0.5. So if we assume that the charge transfer coefficient is 0.5, and if the number of electron transfer is 1, the slope value will be equivalent to 118 millivolt, or yeah, around 120 millivolt per decade. So if it is 2, it will be 90 millivolt per decade. If it is 3, it will be 60 millivolt per decade. If it is 4, it will be 30 millivolt per decade. So which means that lower the TEFL slope indicates that facile is the kinetics. So it is always important to have lower TEFL slope value for your electrocatalysis, which is indirectly indicating the nature of electron transfer, how fast it is occurring. And in the case of HR, it is also sometimes used to predict the mechanism by which the HR is occurring. Usually, if the TEFL slope is around 30, it is said to be following TEFL mechanism, which I have not included here, which will be confusing. So if it is above 40 or 50, it is said to be following warmer Hierosky mechanism. So the methods of deriving TEFL plots are given here. So I have told that you can obtain TEFL plot from voltammogram, CV and LSV. You can obtain TEFL plots from CA or CP. You can also obtain TEFL plots from electrochemical impedance spectroscopy. So here I have taken the case of PTC, one of the best catalysts. In fact, this is the best catalyst so far for HCr in acid, which can start the hydrogen evolution reaction at 0 volt. So I have taken this catalyst and I have obtained a linear sweep voltammogram and compensated the IR drop for the linear sweep voltammogram and plotted against the log current density. I have obtained 42 millivolt per decade. And when I obtained the steady state current for using CA, so I have obtained 33 millivolt per decade for the same catalyst. So when I use this steady state velocity, which is an indirect measure of current density at steady state with no influence of IR drop, is giving us the value of 28 millivolt per decade. PTC is theoretically known to be following TEFL mechanism, which must give a value of 30 millivolt per decade. So in that case, you can see the TEFL plot derived from chronometry and the EAS are very closer to the value which are dictated by the theoretical modeling. But in the case of LSV, you see huge difference. So this arises because of the contribution from other phenomena like capacitance and IR drop. So this is the reason. So this not only affects the slope, it also affects the exchange current density, which will be calculated from it. So that's what I have listed out here. You might have read by this time. So here I'm showing why TEFL plots derived from voltammograms are not so good. So here I have taken the same example of ReO2 modified electrode, and I have taken the LSV that are corrected for IR drop for 100%. But the only difference is that they are recorded with 2 different scan rate. As you can see here, this is the full blue one is recorded at 5 millivolt per second, and the orange one is recorded at 100 millivolt per second. When I plotted this IR drop compensated LSV into a form of a TEFL plot, you can see here the one which was recorded at 100 millivolt is showing 101 millivolt per decade, and the one recorded at 5 millivolt is showing 49 millivolt per decade. So which is true. So how can we be sure? So if we just use the voltammogram recorded at a very high scan rate, and even though you are performing IR drop compensation and plotting the TEFL lines out of it, so which will be true? So the scan rate is seriously having some drawbacks here. So it is always important to use the slowest possible scan rate. So, which was shown by Fabry and co-workers in this report, where they used the cyclic voltammetry, response recorded at 5 millivolt, and the steady state currents obtained with the chronometry. As you can see here, that the dotted line represent the chronometry data, and the solid line represent the cyclic voltammetry curve obtained at 5 millivolt per second. In the linear region where the slope will be measured, there is very good agreement. So as long as you are measuring the or taking the LSV response with the slowest scan rate, this will always be agreeing with the steady state current that you are obtaining with the chronoperimetry or chronopotentiometry. But this will be suitable only for calculating the slope value, not for the exchange current density, because exchange current density is something which is obtained by extrapolating this straight line. So if you just extrapolate this straight line, you will clearly see there is a big difference in exchange current density that you would obtain. So I would suggest to go with chronoperimetry, or it would be even better if you are doing it with impedance spectroscopy. Yes. Yes. Now we have completed the overpotential and Tefl analysis thing. Now we will go to the stability issue. So stability of an electrocatalyst is usually measured or tested or shown using two different techniques. One is CV cycling, cyclic voltammetry cycling, and the chronoperimetry or chronopotentiometry. And I also told earlier that the CV cycling is meaningless because no one is going to perform water electrolysis in real cases just by sweeping the potential. When in real case, they are going to apply a constant potential, constant cell voltage or a constant current density. So in that case, the CA or CP becomes more valuable than the potential cycling in CV. So I have chosen this example. I have taken the same ReO2 catalyst, as you can see here, modified with glassy carbon and carbon cloth. In the case of glassy carbon, the area was 0.0732 centimeter square. In the case of carbon cloth, the area was 1 centimeter square. So in this case, what I have done was, I have performed this chronoperimetry at a potential where the catalyst delivered just 0.732 milliampere per centimeter square and normalized that current density with this area to show it to be 10 milliampere, which is an inappropriate way. I'm just showing it. As you can see here, the scale bar of y-axis in these two graphs are the same. As you can see, the response is very smooth in this case, where I have done the stability with an electrode of very small area. But in the case of the same electrocatalyst with the large area of 1 centimeter square, you can see the disturbance in response. So this is representing the actual case. So this is something this is making ourselves full out of the experiment. So this is not the actual stability test. So I would recommend to perform the stability studies always and almost with an electrode of area 1 centimeter square or higher. So never perform stability studies with a GC electrode having very small area, because that is not going to be the actual response of your electrode at a very high current density, because you are basically in practical measuring the response of your electrode at a very low current density where your electrocatalytic material will experience very low disturbance. But the actual case is something like this. So you must always perform stability test with an electrode area larger than 1 centimeter square. Yes. So so far we have seen overpotential, Tefl analysis, Tefl slope, and the effect of scan rate, effect of IR drop compensation, and other things, and the stability studies with different areas of electrodes. So now we have mass and specific activity. So what is mass activity first? So far, whatever the current density value I have ever mentioned are the geometrical area normalized one. So the geometrical area normalized current density can be highly deceiving because they are not the actual area of the electrocatalyst. So it could be paid attention. So one more thing is that the mass activity. Mass activity is nothing but the current which is normalized by the loaded mass of the catalyst, because current is an extensive property which varies directly with the increasing loading of the catalyst, which means that one can increase the current delivered by his or her catalyst at a particular potential just by increasing the loading. So if you do not mention the loading of your catalyst and you are claiming that my catalyst is able to deliver this much current at this lower potential, it is meaningless. You must also show the catalyst loading. Loading is very important, which has direct effect on the over potential measured. So one better way to do is that you can divide the mass. You can divide the current with the mass of the catalyst, and you can compare. That would be more appropriate. In the case of specific activity, this is very important, even better than mass activity. Here, what we are going to do is we are going to normalize the current by specific surface area. Specific surface area means which can be electrochemical surface area, or some people also use the specific surface area determined from BET analysis. In the case of specific activity, I would recommend you to go with electrochemical surface area rather than BET surface area, because in BET analysis, what we usually do is we are measuring the adsorption-desorption isotherm of a nitrogen gas, and we project some value of surface area, actual surface area. But be reminded that the nitrogen, all the sites that nitrogen adsorbs and desorbs cannot be electroactive sites in the real case. So it is better to use XR for specific activity determination. So here is an example of how loading of a material could be affecting the over potential. You see the same Na3SC4 with the 0.2 milligram loading, you see very low current density. The same Na3SC4 with, here you can see the same Na3SC4 with a very high loading, like 2 milligram per centimeter square, very high current density. So the loading is very important and it should always be mentioned. So now we have turnover frequency. So turnover frequency is the measure of the rate at which the product is formed. In our case, hydrogen and oxygen, which can be calculated using this formula. If you use where the tau is representing the number of active sites, if you use the number of moles of active sites, you can omit the Avogadro number. You can use a simplified formula. Both are correct. So the important thing here is that even though it is an intrinsic activity parameter, the method by which the number of active sites or the surface concentration or the catalyst amount is determined could be very influencing because the method by which this value is determined will vary this value. So there are two different methods. The first one is taking exact number of participating metal sites. This is more precise and tend to be closer to the true values. But in the other case, assuming 100% participation of all catalytic sites, which means that we are not actually paying any attention to the electrochemically active sites or electrochemically accessible sites. We just assume 100% that all our material, whatever we coated on the electrode surface, are participating in the electrocatalytic reaction. This is not going to be the true case, because you will never have 100% participation of all electrocatalytic sites that you coat on your electrolyte. So I would suggest you to go with calculating the exact electroactive sites. In the case of OER, it becomes even easier. So because all electrocatalysts that are known to be catalyzing OER are exiting oxidation or reduction peak just before the OER onset, which is nothing but, if you know the mechanism of OER, you will be very clear of it, because in the first step of OER, the catalytic site itself will undergo an oxidation, forming a metal hydroperoxide intermediate. That metal hydroperoxide intermediate will lead to the evolution of oxygen. So whatever the metal that is getting oxidized before OER onset are going to be the one which will be evolving oxygen. So which means that if you calculate the number of metal sites or catalytic sites participating here, will be equivalent to the number of metal sites or electroactive sites that is evolving oxygen. So you can just integrate the area under this curve, and you can use some conventional calculation, and you can calculate the number of electroactive sites, and you can use this formula to calculate your turnover frequency. So say specific activity and turnover frequency are more important, even though they are not frequently used in water splitting electrocatalysis. They are more important than both over potential determined with the geometrical area normalized current density and Tafel slope and other parameters what I have discussed earlier. These two graphs, the A and B, shows how loading could affect over potential value at 10 milliampere centimeter square normalized with geometrical surface area and the Tafel slope obtained with the same voltammetric curves. So with increasing loading, clearly the power potential decreases and the Tafel slope decreases. Please be remember that this happen only when you are deriving the Tafel plots from the cyclic voltammetric or linear sweep voltammetric response, not when you are deriving Tafel plots from impedance or chronoimperimetry or potentiometric technique. So this is clearly showing that the loading has clear effect on over potential. So how one can have a reasonable or a acceptable comparison? So one way is that calculate the electrochemical accessible surface area and use that as an XR, like I have shown here, and normalize the current, observed current with this XR value. You can see with the 0.2, with the increase from 0.2 to 0.3, 0.4, you don't see any difference in activity. All are overlapping on one another. And the TOF calculated for this are also being the same. So this indicates that specific activity and TOF are truly intrinsic and they never change with the loading. But the decrease in over potential that you see with increasing loading beyond 0.4 milligram per centimeter square is due to the fact that beyond this, even though you are having a higher electrochemically higher number of electrochemically accessible sites, but you are still burying some catalytically active sites underneath the layer of the catalytic surface which is active. So which means that only up to this point the coverage, surface coverage of the catalyst is below 100%. When you exceed beyond 100% surface coverage, you will see this trend. So we should be mindful of that the surface coverage is also important. So besides reporting specific activity in TOF, one should also be mindful of the surface coverage of the catalyst. And here again, the EXA or electrochemically accessible site, they can be determined in various methods, like the one I have said with the redox peak method. And there are other methods which can also be used, which is the double layer capacitance method. This is universal because it is applicable to all type of materials. But because as I said that this is for only OER materials and this can be used for all type of material. But there is a problem with this material, this method, because this is usually done in from CVE measurement made in non-ferrodic region. But other methods include under potential deposition and this is carbon monoxide striping, not cobalt, which can be used for calculating the X of metals like PT, PD, nickel, Ag, and so on. So this is an example where I have calculated the EXA using cyclic voltammetry. You can see I have chosen a very small potential window within which there is no Faradic response, there is no peak. The current increases with the scan rate, linearly increases with the scan rate. And when you plot the difference between anodic and cathodic current against the scan rate, you will get a linear response. And the slope of which is nothing but your double layer capacitance, 2 times the double layer capacitance, which is an indirect measure of EXA. If you want to get the exact value of EXA, you can still divide this double layer capacitance with the specific capacitance of the same material. You will get your EXA value in centimeter square. So basically, this method is applicable to both OER and SER electrocatalysts. Not only that, whatever the electrocatalyst you wish to study, this method is applicable to all. Only problem is that this does not sometimes represent the truly active sites, because this current response, what we use to calculate EXA, is taken from a region where no charge transfer is occurring. But on the other hand, in our case of water electrolysis and water splitting, the reactions which take place are purely electron transfer reaction. So this could be a controversial thing in this method. Moreover, this method can be used to compare 2 different catalysts from the 2 CDL value, or you can compare the same catalyst before and after a certain operation. That could be CAR, CPR, cyclic, something else. So you can show what is happening to the electrochemical active surface area. So before and after some electrochemical experiment, and you can also compare 2 different catalysts. And then this is something new which I have used in my recent study. The results are not published, so I'll quickly tell about it. So we have developed a tungsten-based HER electrocatalyst where we found that the aerial current density is overwhelmingly high. So we wanted to find out the actual electrochemical surface area, for which we initially planned this method, the CDL method, But as I explained earlier, it is not the actual electrocatalytic side which is participating in the electrocatalytic reaction. So we have decided to obtain impedance spectroscopy at catalytic turnover condition, not in the non-Faradaic region, which will show you from the phase angle plot, you can find out the theta max, the phase shift, maximum frequency at maximum phase shift value, which will, for which we can also get the specific capacitance and the double layer capacitance, which is nothing but the constant phase element. So by dividing the constant phase element with the specific capacitance, you will get the EXA, like the one what we have obtained. And when we use this EXA value to normalize the current density, we got some reasonable comparison. So this is another method which has never been reported. This is the first time, which will be soon published. And we finally have the Faraday efficiency, the selectivity. Selectivity is very important because if you have a catalyst which is capable of delivering very high current density and also by having better kinetics, but if you're not sure about whether the applied energy, that is the electric energy that we are giving, is exactly and completely used for the electrochemical conversion that we are desiring or not. This is very important. So reporting selectivity of a catalyst is very, very important. This can be done in two methods: conventional method, where you can experimentally quantify the amount of gas evolved using GC, and you can also theoretically calculate the amount of gas evolved from the chronoamperometric or chronopotentiometric curve, and you can use this formula to calculate the Faraday efficiency. This is an example reported by Professor Day of ISCS, and you can use the rotating ring disc electrode for OER. This is applicable only for OER. These two are example of nickel hydroxide and cobalt sulfide OER catalyst we used recently. So in this case, you will use this formula to calculate the Faraday efficiency. But I'll tell you something that in case of OER, you cannot have a catalyst which will have 100% Faraday efficiency, because all OER catalysts must have to undergo self-oxidation before performing OER. So some amount of energy needs to be dissipated for the self-oxidation of catalytic site. So in case of OER, if you have 90 to 95% of Faraday efficiency, it is okay. So in the case of HER, it is always expected to have 100% Faraday efficiency, because there you are not letting your catalytic site to undergo any side reaction like when we do in OER. So now I have explained in detail about the electrochemical impedance spectroscopy, the fundamentals previously. Now we will see how appropriately we can use this technique in water splitting electrocatalysis. The main purpose why the electrochemical impedance spectroscopy is used in water splitting is to compare the activity trend. So if you are studying a set of given catalyst, you have to always give the electrochemical impedance data at certain condition, which will show the activity trend in parallel agreement to that of the one you witnessed with voltammetry and chronoamperometry. So other things that can be obtained from EAS is you can get CDL, you can calculate EXA at catalytic turnover condition, which is very important, not in non-Faraday region. And we can also use it for deriving TEFL, and we can also use it for calculating exchange current density, which is nothing but the 1 by RCT value, area normalized RCT value at onset potential. So one thing is that in using electrochemical impedance spectroscopy in water splitting electrocatalysis, people use different convention. So some people use performing EAS at onset potential. Some people use performing EAS at the same current density for different set of catalysts. Some people perform EAS at OSCP, and some people perform EAS at fixed potential beyond onset. That is in catalytic turnover condition, where all studied catalytic interfaces are having certain activity. Okay, so what we have done is we know that there exists a confusion about using how appropriately using this EAS in water splitting. So we chose a set of electrocatalysts, OER electrocatalysts, which are having different activity. So, and we performed EAS measurement at all these conditions and compared their result. So this is the catalytic interface we have taken: stainless steel, cobalt, nickel, and copper foils. So before activation, you can clearly see that the activities are different at all potential, you can see. But the problem with these metals are they tend to evolve hydroxide and oxide layer upon OER. So we wanted to oxidize the metal by chronoamperometry kind of activation. So we activated it, and after that we have seen that the activity is still different. And in the case of cobalt and stainless steel, at higher over potential, they are almost the same, but in lower over potential, the activity difference is still witnessed. So we have taken this activated files of stainless steel, cobalt, nickel, and copper and analyzed the EAS measurement at this condition. So first, let me talk about the measurements made at 0 volt versus OCP. I have told that the OCP, measuring impedance at OCP is very important in case of battery, supercapacitors, and also in corrosion prevention studies, because people want to know the exact nature of the interface, whether it is capacitive, resistive, or it can be facilitating the charge transfer. So it is okay. It is appropriate to use the 0 volt versus OCP or at OCP in batteries and supercapacitor study, as well as in corrosion prevention. But in electrocatalytic water splitting, it is not so, because at OCP or at 0 volt versus OCP, no desired reaction is actually occurring. So when you perform EAS measurement at this potential, you are not actually monitoring the electrocatalytic reaction that you wish to study. So the RCT value that you observe will not be in agreement with the activity trend that you obtain with the LSV and other things. So this is a simple thing. I have also given the OCP value along with the Nikos plot. As you can see that stainless steel and nickel, they exert different OCP before activation, after activation, and after activation plus 30 seconds rest. So this indicates that the OCP is keep on changing. So we cannot rely on this measurement for comparing the activity. In the case of cobalt and copper, their OCP is increased, but when rest is given, they return back to the original OCP. So when we compare these 4 electrodes having different characteristics about their OCP, so how can we make a rational comparison of their activity trend? So OCP measurements will not give you anything about the activity trend. So according to the LSV, I have shown the activity of, so the order of RCT should be like this. Stainless steel should be the one with the lowest RCT and copper should be the one with the highest RCT. But if you see here, surprisingly, the copper is the one with the lowest. So this is clearly showing this is not the way to measure the activity trend in terms of impedance analysis. So I have done for another technique where the constant potential before onset is used, because I have told that OCP is nowhere near to our actual potential where the desired electrocatalytic reactions are occurring. So what if we do the electrochemical impedance spectroscopy analysis at a potential which is very near to onset potential? Some people use this one. So I have tried this one too, but I didn't get any meaningful result out of it. Even if you see this, this is not in accordance with the expected order of RCT. So again, this practice is not correct. And we have also compared the activity trend at different potentials for the catalyst for different potentials, but the same current density, like over potential of 25 milliampere per second. So all these catalysts are delivering 25 milliampere current density, but at different potential. In that case, the expected order is something different. But if you see this, cobalt is accepting the lowest RCT, and stainless steel comes next, and copper comes next, which is the lower, which is the one which delivered a very low current density. The nickel exerts a very high RCT. So this is also another good practice for comparing the activity trend, because it is also not exactly reflecting the actual identical electrochemical interfaces. So finally, we have the Nikos plots obtained out catalytic turnover condition. So what I have done is catalytic turnover condition is nothing but the potential region which are coming beyond the onset potential. So beyond 0.5. So I have chosen this potential 0.6, 0.65, 0.7, 0.75, like this. I have measured the RCT. As you can see that the RCT is keep on decreasing with increasing potential. So this is clear. So this is the same trend is observed with all 4 catalysts. So now what we have to do is compare this catalyst at the same potential. So that's what I have done here. So this is the plot of current density versus potential. You can see the current density is increasing with increasing potential, which means that the RCT should decrease. So as you can see, the RCT of stainless steel is decreasing, and next comes the cobalt Next comes the nickel, and finally the copper. So this is the convention which is exactly reflecting the activity trend that we are expecting from the LSV that I have shown. So this is very clear that whenever you want to compare a set of electrocatalysts, given set of electrocatalysts, and you are having confusion where to perform ES measurement, please be remember that, being reminded of that, you should always perform ES measurement at catalytic turnover condition at the same potential, irrespective of the current density delivered by the catalytic interface, because that is the actual difference between your catalyst, right? So you don't have to worry about the difference in current density. Please be reminded that you have to do always perform ES measurement in catalytic turnover condition. Yes. So that's all. I would like to summarize the things I have said. As I told here, in case of CV and LSV, using IR compensation only for TAFL. So uncompensated value is also important. In the case of C and CP, use this for TAFL plot and perform stability at high current density at high over potential. Always use electrode area higher than 1 centimeter square. And EAS, I have just summarized, never use EAS measurement made in regions other than catalytic turnover condition. In this method, you can get most accurate TAFL lines and CDL, XA, and other things. So when you report your electrocatalyst for HER, OER, so check yourself that whether you are reporting all this value. Over potential at geometrical area normalized current density without IR drop compensation, of course, and specific activity, mass activity, TAFL slope and exchange current density, turnover frequency, Faraday efficiency. Apart from that, you should also report the stability. So these are the things. And if you like to know more, you can read my reviews and articles, which I have listed here. Yes, I hope this talk have been useful to you. Yes, we are also open for collaboration. We basically work on electroactivation of small molecules, whatever small molecule that are important in energy and environmental science and technology. So if you think that you have a interesting material with the surface and structural characteristics, and if you think that you have done some literature survey, and if you think that this can be used for some electroactivation of some small molecule, you can always approach us. Please write to us to this email ID, and we believe that the best idea can happen only when the two minds joins. Yes, and I wish to acknowledge my funders. First, I would like to thank Japan Society for the Promotion of Science, who awarded the prestigious JSPS postdoctoral fellowship in 2019. So I also would like to thank CSIR, who have given me the funding support through JRF and SRF fellowships and during my PhD course. And I would be thankful to these people who are being there with me for all my needs in my current workplace. And this is Professor Noda, who is a nice person. He is always there for me to encourage in all situations. And I should not forget to acknowledge my former mentor, Dr. Kundu, and his group. And without them, I could not be here. And I must thank all my coursework tutors, advanced electrochemistry coursework tutors, Professor Vijayamohan K. Pillai, Dr. V. Ganesh, Dr. J. Madhyarasu, Dr. Sheila Begmans, whoever taught me these things in electrochemistry, whatever I have just shared with you. I'm very thankful to all of them. I hope this talk have been useful to you. And if you have any query, you can ask me now. Thank you.
Thank you so much.
Yes.
And I would like to know any questions from the participants. They can raise their hands. A few questions which we got through the YouTube that I will be asking Shamim Abdul. He has asked CV curve how much we are controlling oxidation and reduction. I will post the question in the Zoom, and the presenter can answer that.
Sorry, I didn't. Can I
Yeah.
can I see the question, because I couldn't hear you properly?
Yeah, I have posted it.
Yeah, wait a second. Where can I see it? I don't know. Sorry. Yeah. In the chat box?
Yeah.
Yeah, okay. Yeah. CV curve. Yeah, Shamim Abdul Samadin. Okay. CV curve, how we are confirming? Oh, sorry, it is changing. Keep on changing. sorry. So I cannot see it.
Yeah, I
Sorry.
have shared
Yeah.
the screen now.
Okay.
Yeah.
Yeah, okay. Yeah, this is perfect. Yeah. CV curve, how we are confirming oxidation and reduction? Why in some cases both peak are not same? Yes, and this is a good question. So when we can say it is oxidation is when you polarize the interface anodically. Anodically means when you apply positive potential. The only possible reaction is that you are oxidizing your material. So the current density will be in positive direction according to the IUPAC convention. So when you polarize the interface to the cathodic side, the current density will be in the negative region. So from this you can come to know the process is either oxidation or reduction. Why in some cases the peaks are not same, right? This is very simple. I told that only chemically and electrochemically reversible reaction can have the same peak current because their ratio is always going to be 1. When your reaction is quasi-reversible or irreversible, they will not be the same. So that is the case in most of the experimental electrochemists who usually encounter. So I will be talking about that in my upcoming webinar. If you are interested, you can register there. I will be happy to explain you there. And Satyam Sri, what is the minimum amount of energy required by sun to split water? So uh, I would put this question in a different way. I guess he wanted to ask using solar energy, right? So I don't have an idea about the amount of energy that we are receiving from solar. If you ask this question to a person who is working on photoelectric water splitting, he will say. But the convention we use 10 milliampere per centimeter square in screening the performance of an electrocatalyst is because that represent the solar to fuel conversion energy device, the energy device's performance equivalent to 10%. That is the reason why we use 10 milliampere per centimeter square. But I don't have an idea about the sun to split water. And Balaji M, how can we select photocathode or photoanode material for water splitting? I'm really sorry, I'm not an expert in photo or photocathode or photoanode material. I guess photoanode is always better because forming a photocathode is practically a difficult method. A friend of mine told me this thing. So I would request you to refer some good review on photocatalytic water splitting. Balaji again asked, during photochemical reaction, the required photovoltage is only 1.23 volt, or we require any more initial potential for water splitting? Yes, Balaji, you will be requiring additional potential because by definition, the 1.23 volt is determined by considering the thermodynamic aspects of the water splitting reaction. There we also have kinetics, which I have explained clearly that you will always need additional potential. So if you have a material photocatalyst which is having approximately similar band gap to that of 1.23 volt, you will not be able to split water because all the photocatalytic material which are being used so far, I, I know they always have a band gap over 2.2 or 2.1 or 2.3 something. So you will be requiring higher over potential in the case of photocatalytic water splitting too. And Balaji again, kindly share any practical difficulties while doing the photochemical. No, as I have not done any photocatalytic study so far, so I'm sorry that I could not help you with this. Arjun Anita, which group of material in periodic table it is very suitable for photocatalytic activity? Again, the same question from guy interested in photocatalytic water splitting. I would say any photoanode. It can be zinc or zinc-based oxide or titanium oxide or bismuth vanadium oxide or tungstate, molybdates, and these things have been experimentally tested for photocatalytic water splitting. You can check that one. Vinod Kumar. Is it possible to get energy from leather industry wastewater by this method? Oh, I couldn't get this question. Is it possible to get energy from leather industry wastewater by this method? So I will put it in another way. I think Mr. Vinod Kumar wants to ask that this method can be used for treat wastewater of a leather industry. I guess yes, because we are basically oxidizing the water, so which will also produce molecular oxygen in the water, so, dissolved oxygen, which can be useful in degrading the organic pollutants. D-gromol. Why high specific energy material is needed? It's because of a simple reason. When you combust it or convert it electrochemically, it will give you higher energy. That is the reason. And is there any fire explosion occurring during water splitting reaction? Oh, okay. Fire explosion can occur only when you have both hydrogen and oxygen together at certain pressure and temperature. But in the explosion range of hydrogen and oxygen is quite large, because with hydrogen to oxygen ratio of 4 to 95%, you can see explosion, but you need some amount of pressure to be applied. So in the case of conventional electrocatalytic studies, what we study here, we never experienced explosion. So there has been nothing sort of that happened so far. And Satyam Shri, the amount of photon which is coming from sun is not constant at all time. Yes. So how can we clarify and identify energy required? Yeah, that's why people use solar simulator in lab, which will give you one sun energy. I forget the amount of energy in joules. They say that is one sun illumination. Please refer some photocatalysis review. You can get that one. How can we scale up this technique? Satyam Shri, I remember you are from Sikri and you are a chemical and electrochemical engineer. Scaling up is your process. Inventing the process is my process. Okay, thank you. And Ajit Singh, please mention the book you told to read chronoamperometry. This is by Electroanalytical Methods by Alan J. Bard and Laurie L. Faulkner, which is a very famous book. You can download the PDF, which is available you can get it from the simple Google search. And Sangeeta RIS, photoelectrochemical measurement is same as electrochemical one. Yes, almost. But only the difference is that you will be applying artificial solar illumination. Like I said in my previous question, you will be also applying light to the anode, or if it is a photoanode, to the cathode if it is a photocathode. Remaining is same. And Dr. V. Srija, whether the inert atmosphere is needed during electrolysis. I never used, because the gas what we are producing, hydrogen, and the gas what we are evolving at anode oxygen, they don't need to be preserved in inert atmosphere, because they are already inert enough to be remain in their molecular state without any problem in room temperature and ambient condition. Karupaswamy Balasubramanian, I see only the name, but no question. Is there any more question? Yes. Why both reversible and irreversible reactions, the starting and ending points are not same? I don't think so. The starting and ending points, I guess you are asking about the potential. The starting and ending points of the cyclic voltammogram is something that we determine, not that the system determine. I think you are asking about the peak potential, right? In the case of reversible reaction, the peak potential will be separated by 59 millivolt per 59 millivolt peak to peak separation. In most cases, which is very difficult to obtain. If you still have something like 70 to 75 millivolt, it is still a good value, and you can claim that your reaction is reversible. But in the case of irreversible reaction, the question itself saying that the reaction is irreversible, so you cannot see the peak position at the same potential. And moreover, you should also be mindful of the diffusion layer formation, which I have explained, because if there is a diffusion layer formation, that will again affect the position of the peak. So which I have explained there, and you can write to me if you have further doubt. And as the water is the abundant material on earth, so we are getting hydrogen, lightest and not pollutant, as fuel by water splitting. But naturally, we don't have pure H2O. Yes. And I will tell you something, that we don't split pure H2O, because pure H2O is something very resistive. It is having 18.2 mega ohm, I guess, per centimeter square. So you cannot split pure water without applying additional extra energy. So that is why people always perform water electrolysis with either highly acidified solution or highly alkaline solution to facilitate the process of water electrolysis. And then from Deepika, I'm working on MnO2 with the Fe doping. How to select different doping combination in an aqueous medium? This is something that you must ask a material chemist, not an electrochemist. Okay, but what I guess is that Fe, from my experience and from the things that I know about Fe enhanced OER, Mn oxide, manganese oxide, is not the suitable host for Fe. in order to see some reasonable enhancement in the OER activity. I'm sorry that I could not help you with the ways of different doping level, but I guess you can get this answer somewhere else. And yes. Rebecca, sir, can you please explain which parameter can be interpreted from body plot? Yes, we have two different body plots. The one is body impedance plot, from where you can get the precise value of solution resistance, that is uncompensated resistance, and the RCT. And you can also, from the linear portion, you have in body impedance plot, you have something called the Z-shaped line, right? In the Z-shaped line, the line which is having a slope, you can measure the slope actually. The slope, if the slope is 1, that is exactly the reversible reaction. And if the slope is lesser than 1, like 1 by 2 or 1 by 3 or 3 by 4, we can say the reaction is being dictated by the diffusion process. And you can also do one more thing from body impedance plot. You can extrapolate the linear line to the lowest frequency of the imaginary, modulus of impedance, where you can get the 1 by impedance value, which is nothing but the admittance, which will say you the electrochemical active surface area at the catalytic turnover condition. And yes, Mohan Raj to everyone. I did E. coli form analysis for calculating the efficiency of sterilizing. At the same time, I don't know what mechanism acts to kill E. coli due to the complexity of the disinfection process. It is difficult for me to pinpoint the exact mechanism. Can you please explain it? And I would be able to if you have precisely mentioned the condition, like the pH and the solution, the type of electrolyte present in it. And I guess you are disinfecting the medium just by creating an oxidant or reactive oxygen species in the solution, which will kill the E. coli, I guess. So the reactive oxygen species that you are generating for killing the E. coli is highly sensitive towards the pH of the medium and the electrode material you use and the potential you apply. So many other factors I need for answering this question. Ranjit to everyone, is electrochemical water splitting is a viable technique for hydrogen production? Yes, that's what I told. It is not a viable technique because water splitting requires high amount of energy for the counter, the unwanted, I can say, unusable or the not insignificant counter reaction, oxygen evolution reaction, which is taking up more energy, which is also causing the huge energy loss. So when you combine hydrogen again in the fuel cell, you are going to lose similar energy loss. So in that sense, in energy efficiency, I would say that the steam reforming of hydrocarbon is still the best method for generating hydrogen. But when you see, when you consider about the purity of hydrogen produced and the ease of operation, I would say water electrolysis is better. And one more thing is that now people are trying to replace this operationally insignificant oxygen evolution reaction with the chlorine evolution reaction, which can also be used for generating hypochlorites and sometimes hydrogen peroxide. So you can make water electrolysis a profitable reaction. Yes. Any more question? John Rodney. Sir, could you explain the impact of bubble formation over the catalyst during the splitting process? Does that bubble formation have an impact on VRHR and TFL? Yes, of course. It does have. Because when you have bubble formation and the bubble does not move out of your catalyst surface, you are basically masking the catalytic sites with the bubble which have been formed on the surface. So your activity will be lower and you will be underreporting your catalyst. So it is very important to ensure that the gas bubble is leaving out of the solution immediately, which you can ensure by performing the experiments with the RDE setup, or you can stir the solution, or you can simply apply low power ultrasonic waves. Be sure that the power of the ultrasonic waves that you apply is very, very low. Otherwise, your catalytic material will peel off from the substrate electrode you use. So be careful when you use ultrasonic waves. And Prakash Natarajan, which electrode system is good for HAR and OER, 2 or 3 electrode system? Yes, when you study only the off-cell reaction, you always use 3 electrode system because that is the standard to report the catalytic performance. But when it comes to water electrolysis, I mean the full total water splitting, 2 electrode performance is more practical. So that is reflecting the actual case of the electrocatalyst when it is, which will reflect its activity when it is applied to actual water electrolysis. So if you are having a bifunctional catalyst, you study the electrocatalytic performance using 3 electrodes for both off-cell reaction, and then you also perform total water splitting, making it 2 electrode cell. So you report both of them. It will be useful for the reader to estimate the performance of your electrocatalyst. Shubham Chatterjee, Anna, is it possible to produce a better catalyst than PTC? Of course, actually there are better catalysts than PTC, which also use a very tiny amount of PT, but not entirely PT. Something like Fe cobalt PT alloys are there. They deliver better current density than PTC, and also very recently the evolution of phosphide material. Some iron phosphide and cobalt iron phosphide, they deliver better activity than PTC. And we also have ruthenium, which is capable of delivering equivalent activity to that of PT for HCr. In alkaline, even ruthenium outperforms PTC. So, any other question?
Okay, I thank
Yes.
the participants for the questions. The
One
questions
more.
are overflowing, I think.
Yes. And one more question, I will answer the question from Janani Jnanaprakasam. Thank you for the informative talk. What do you think about the active sites in NiSe4 for HCr or OER? Do nickel foam has effect in catalytic activity? Yes, it will have effect in catalytic activity when the nickel selenide grown-on nickel foam has surface coverage lower than 100%, which means that you are also exposing some part of nickel foam to get into contact with the electrolyte solutions, which means the nickel foam will also participating in the electrocatalytic reaction. You should ensure one thing that there is no further oxidation of nickel foam and only the nickel selenide is in contact with the solution. So in that case, you can avoid the contribution from nickel foam. And yes, thank you. We can conclude it. If you have still doubts, you can write to me the email I have shown in my final slides, and we are also, as I said, open for collaborations. So if you think that you have an interesting material, you can send it to me. I will assess with the help of my team, and we can have some fruitful result out of it. And thank you very much for your patience. And I also thank Savita Engineering College and Department of Physics and Dr. M. Priya and my good friend Satyamurthy for giving me this opportunity. I thank all of you for peacefully listening to me so far. I hope this has been some use to you. I hope to see you all again in my next webinars too. Thank you very much.
I thank all the participants and I thank the presenter, especially for a wonderful presentation for 2 hours non-stop. It was overflowing with the presentation and details and information. Thank you so much. And let us organize another program with you, presentation
sure,
with you.
I would be happy to.
Okay. Thank you so
much. Thank you, madam.
We will be sending the feedback form through mail to the participants, to all the participants. And the recorded also, we have recorded the entire session. We will be sending it also to the participants. And for any questions or queries, you can send a mail either to the same mail ID you have registered or to Dr. Anantharaj. And thanks a lot for everyone. Thank you so much.
Yeah, thank you, brother. Yeah.